Hello, welcome to my third series, Algebra 2 and Pre-Calculus. As I said with the geometry, I have my old Algebra 2 and Pre-Calculus videos in the playlist titled Old Videos. You can always access them if you want, but this is my new format, so it'll be shorter videos. So instead of covering all of the review in 2 videos, I would just split it up into topics. So this one would be mainly sets, next one would be about real numbers, and so on. But that's basically all of my introductions, so we can get right into sets. Fun. So a set is basically a collection of objects. And each object is called an element. So we have sets, and we have elements in those sets. And I'm purposefully writing elements away from sets because I'm going to use this word sets in a moment. But for now, I'll give you an example set. Let's say the set S is equal to 2, 3, 6. The elements in this set is 2, 3, and 6. All 3 of these are elements. Now, we can use some notation with this. We can say every element in this belongs to S. And the belongs to can be written as a symbol that looks a bit like a backwards E, but not actually. It's more curved. This, we can write something like 2 belongs to S. And this symbol means belongs to. We can also write does not belong to if we just draw a slash through it. So we can say 9 does not belong to S. Those are some symbols we can use with S. Now there are 2 different types of sets. Infinite and finite. As you can probably assume, infinite sets have no end. They go on with infinite elements. And finite sets have an end and they have a finite number of elements. So that's why I wrote elements all the way over here, so I have space for infinite and finite over here, the 2 branches of sets. And that's that. And we can also write sets using set builder notation. So this is just normal notation. We can also use set builder notation. So I'm just going to move this up here. Oops. Actually, I'll just delete it and write the set again because I want to show you to write a set using set builder notation. So we write a set S is equal to 3 times x, where, and the where is represented by this. It could be represented by a comma, but most of the people write the bar, so I'm just going to write the bar, where x belongs to all natural numbers. So for those of you who don't know what natural numbers are, we're going to cover natural numbers in our real numbers video, but for a brief overview, it's basically just the numbers 1 to infinity, 1, 2, 3, 4, all the way to infinity. Those are the natural numbers. So if we want for x in natural numbers, that means every one of these numbers can be x at some point. And if we want 3 times those numbers, then 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, and so on. So S basically is an infinite series containing the numbers 3, 6, 9, 12, and so on, all the way up till infinity in this pattern. So that's a set. And we can write the same exact set using set builder notation. So now there is a few more things related to sets. I can get rid of all of these, and I can also get rid of the element, and infinite and finite. So there are a few more things. There's something called a universal set U. And it basically contains all elements in the discussion. If we're talking about species of crows, then the universal set contains every single one of those species. If we're talking about the people on Earth, there's a 7 billion long set that contains every single person, and it keeps on changing, of course, because the number of people and the people themselves change on Earth. But that's a very long set. I don't have space to write all of it down here, but it basically contains everything in discussion. The opposite of that is called the null set. It basically contains nothing. You can represent it with this. You can also call it an empty set. It basically contains no elements. So this, it's easy to write. It's just open brackets, close brackets. These are 2 important sets as we're going to be talking about Venn diagrams right now. So we would have to use universal and empty sets soon. A Venn diagram is basically a diagram that represents sets, and most people have seen Venn diagrams that look like this, or I can also actually create circles like this, so it's easier to see. I'll probably just erase these ones. So we can use Venn diagrams to represent sets in the following ways. Basically, different terms relating to sets. Each Venn diagram can represent a set. Even this is a Venn diagram that just represents one set, and we can have all the natural numbers in it, for example, now that you know what those are, and so on. That would be a set. And then we also can represent other terms with it. So there's something called a subset with this symbol. It's kind of like a sideways U with a bar under it. It's basically where every element of A is an element of B. So given two sets A and B, every element of B, or every element of A is a element of B. So if I have the set 1, 2, 3 is A, and I have the set 1, 2, 3, 4 is B. And then A and B are subsets. A is a subset of B because 1, 1, 2, 2, 3, 3, and meaning every element in this is an element in this. We can use Venn diagrams to represent this. A big circle represents B, and a smaller circle inside of that, completely inside of that, represents A, because a subset is basically something that's completely inside another. Some important rules about subsets. We know for a fact, these are properties of sets, that A is always a subset of itself, and a null set is always a subset of any set. So basically, any set's a subset of itself. Null set is a subset of any set. So that is subsets. We can use Venn diagrams to represent subsets. And there's a few other things we can use. Equivalent sets is basically when A is a subset of B and B is a subset of A. Basically, they have the same elements and the same number of elements. So 1, 2, 3, 1, 2, 3, they're equivalent. Now, we also have complements. We can also use Venn diagrams to represent complements. Let's see if you can understand what a complement is by this picture. Probably not, but let me label A as this and U as this. Some of you may not know what U is, but I just covered U in a previous part of this video. So if you don't know what U is, watch a few minutes earlier, and U is basically the universal set. It contains all elements in discussion. So the complement of a set A is basically everything that's in U but not in A. That can be represented by A prime. So there's this little apostrophe up there that signifies it's A prime. So that's the complement of a set. We can also do the intersection of two sets, and this is where you see most Venn diagrams, something like that and then like that. The intersection is this part. So let's say we have A and B. The intersection of them would be A intersection, this upside down U, B. It's basically all elements that belong to both A and B. And we have intersection, we also have something called union. Basically, given two sets like this, union is everything in both sets. So all elements that belong to both A or B, and it's represented with a U. And finally, we have disjoint sets, sets that have no intersection. So it's also related to intersection, except for the fact that they have no values in common. They have no elements in common. And there's no symbol to represent this, but we just know that A and B are disjoint. So that's a brief introduction to sets. Sets are pretty important in algebra because you have the natural number set, you have the real number set, and so on. We'll actually be talking about real numbers next. But for now, this is just a review of sets. We're getting close to 10 minutes, so I'm just going to end this video here. If you have any suggestions, let me know in the comments below, but see you in our next video.